A type of adsorption chromatography, usually abbreviated to TLC, which uses layers of adsorbent spread out on glass and separates on the basis of polarity, meaning the extent it will absorb onto a solid supported stationary phase and dissolve into mobile phase, is driven by the decreases in free energy that follows once the solvent enters the pores of the stationary phase. TLC is very similar to paper chromatography and is also a linear method, but TLC is quickly reducing paper chromatography in labs as TLC is generally more reliable and plates becoming cheaper and more readily available. Preparing a TLC plate is very similar to preparing a paper chromatograph. A small amount of sample is dissolved in the minimum solvent and put onto a pencil line around 1 cm from the bottom of the plate using a TLC spotter, which is a thin glass tube that is marginally thinner at one end, so holds a small amount of sample. The spot is allowed to dry and the plate is put in a container with a shallow level of solvent at the bottom and covered. The solvent is allowed to rise until it is almost at the top, around 3/4 of the way up, and is then lifted out and a pencil line drawn where the solvent front was. The plate is lifted out and the solvent allowed to evaporate, and the RF values are measured in exactly the same way as paper chromatography. Some plates even have a pre-adsorbent zone that holds sample until preparation begins, in which all components that are soluble in the solvent system pass through and are then focused into a narrower band before entering the chromatographic layer. This gives you better resolution between spots. As in paper chromatography, the mobile phase is a solvent and again can be virtually any liquid. Depending on the choice of mobile and stationary phases, the separation can be run in two ways. Normal phase, which is where the adsorbent strict stationary phase is more popular than the solvent system mobile phase, and reversed phase, which is where the stationary phase is less polar than the mobile phase. Polarity of the mobile phase can have a great effect on the quality of your results and can sometimes be a bit problematic. In the case of TLC, if the sample to be analysed is a polar reaction mix and the non-polar solvent is used on a polar stationary phase, the solvent will not be held strongly, and when the solvent meets the reaction mix, there will be an attraction. The non-polar solvent will not be able to overcome that interaction, and so the components will not move and you will get no spots. Alternately, a really polar solvent is used instead. It will absorb strongly to stationary phase and will displace all the components it comes across. This will cause everything in the reaction mixture to move all at once, and so all spots will be at the solvent front. The best approach for TLC is to start with something non-polar like hexane and slowly add increasing amounts of polar solvents like, say, ethyl ethanoate. There is also a lack of control with the mobile phase, which could cause problems with consistency because flow rates depend on the viscosity of the mobile phase, the surface tension, and the nature of the stationary phase, as well as the temperature, which is problematic due to the fact that the first adsorption of a component is exothermic and raises the temperature of the solvent front. Stationary phase for TLC is small particles of porous adsorbent coated onto a flat, inert, solid support, and the transport up the plate is due to capillary effect caused by these pores. The recommended thickness of the adsorbent plate is around 150 to 250 micrometers, and if making your own plates in the lab, the uniformity provided by a spreader is advised. The two most common adsorbents used are silica gel and alumina. Silica gel has the chemical formula SiO2 and is generally used for a broad range of organic and ionic reaction mixtures. It is made by the spontaneous polymerization and dehydration of salicylic acid generated by adding sodium silicate solution, resulting in an amorphous solid with a large surface area and pores, and can be modified to become more polar by adding specific complexing ligands or alcohol groups, or less polar by adding alkane chains and benzene groups. Alumina has the chemical formula Al2O3 and is available in acidic, neutral and basic forms. The acidic form is the least active of the three, but is good for separating acids. The neutral is good for strongly absorbing groups like esters, ketones, and the basic is good for almost all basic and neutral compounds. Industry and demand for more accurate methods has resulted in there being a few variations on the basic technique of TLC that are worth mentioning. HPTLC, or high precision thin layer chromatography, is the term used when the adsorbent coated onto the plates has a smaller average particle size and narrower particle size range. These special plates are capable of getting a high resolution between the components, as well as rapid running times, which are often over shorter distances than conventional TLC. This increased performance is partially due to the fact that HPTLC, the atmosphere around a chromatogram, is kept totally constant, especially in regards to vapour pressure, which removes quite a lot of the issues discussed in the mobile phase section beforehand. Overpressure thin layer chromatography, or OPTLC, is a term used to describe any TLC separation during which the solvent is forced by applying external pressure. The forcing the flow optimizes the mobile phase velocity over nearly all the separation distance without losing resolution. OPTLC plates are covered in an elastic membrane under external pressure, which also allows for the conditions to be better controlled. TLC has many limitations that paper chromatography has, like the fact that similar compounds can have similar RF values, or some components may not have a reference value to be compared to. TLC is ideal for small-scale separation and to track progress in the labs using a few plates during a reaction, but it would not be suitable for large-scale separation, or under or overloading can lead to difficult-to-interpret results. That being said, it is still one of the easiest and cheapest methods and is almost completely non-destructive to samples.